In this video, we are going to talk about the series LCR AC circuit. So from the name itself, you can understand that there are three elements: the inductor L, the capacitor C, and the resistor R. All of them are connected in series. So what we are going to do is we will find the relationship between the EMF and the current. All right. So before we do that, I want to just go back to what we have already discussed before, and let us look at the phasor diagrams of those elements one by one. So we have discussed that the phasor diagram of a purely inductive circuit, that means a circuit containing only the inductor, is something like this. All right. The current I naught is lagging behind the applied EMF. Or in other words, we can say that the applied EMF is leading the current by an angle of 90 degrees. I think you remember, right? These phasors are what they are: anti-clockwise rotating vectors, as can be seen by the direction of this arrow. So you see the current is here, but the EMF is already rotated by an angle of 90 degrees. So therefore, we can say that the EMF, the peak value of the EMF in an inductive circuit, leads the peak value of the current by an angle of 90 degrees. Similarly, in a purely capacitive circuit, we can see here that the current is leading the EMF, or we can say that the EMF is lagging behind the current. The EMF is here, but the current has already rotated by an angle of 90 degrees. So therefore, in a purely capacitive circuit, the peak value of the EMF is lagging behind the current by an angle of 90 degrees. And in the case of a purely resistive circuit, the peak value of the EMF are in phase. Therefore, they are going along the same line. Okay, they are in phase. There is no phase difference between them. All right. So what we are going to do here is, let me first draw the circuit. So in figure 1 here, you can see that there are three elements: the inductor having an inductance L, the capacitor having a capacitance C, and a resistor having a resistance R. VL is the potential drop across L. Vc is the potential drop across C, and Vr is the potential drop across R. Okay. Now VL, VR, and VC, they are the peak value of the potential drops across L, R, and C respectively. Okay. Now just have a look here. This phase diagram, what we are going to do is I am going to rotate this phase diagram. I'm going to rotate it in this way, so that the current now will be pointing along this direction and the EMF will be pointing along that direction. But this peak value of the EMF in a purely inductive circuit, let us denote it with VL. All right. So if you look at this diagram, VL I naught here, you're getting this diagram here. Is this clear here? So this diagram and this diagram is exactly the same. Only thing is I have rotated the phasors like this in that direction, so that the current will be pointing along the x-axis. Similarly here, what I will do is I will rotate this phasor diagram in that direction, so that the current will be pointing along the x-axis. So therefore this E naught now will be pointing in that direction. Got it? But then instead of E naught, we will write here VC. What is VC? VC is a peak value of the EMF in a purely capacitive circuit. So we are getting this kind of a phasor diagram. And for the phasor diagram for a purely resistive circuit, I'm going to rotate it like this, so that the I naught and E naught will be pointing along the x direction. So I'm getting this kind of a phasor diagram. Is this clear here? So I think you should not be confused between these phasor diagrams that I've drawn separately for L, C, and R, and these phasor diagrams that we have obtained in the theory when we discuss LC and R circuit individually. Okay, it's just the same, it's just a modification. All right, in reality the phasor diagram looks like this. Okay, it looks like this, but what we are doing here is we are just rotating it so that we make the I naught all pointing along the x-axis. Got it? Okay, so if we do that, we will get these kind of phasor diagrams. Are we clear here? Then next, what do? I take this phasor diagram and I put it here. And I put it here. You see, so this VL is from here till here, is denoted by OB. And I naught is denoted by OX. I take this and I put it here. VC is now denoted by OC, I naught by OX. I take this and I put it here. VR here, not R. This is supposed to be VR. This will be not that. VR is along OA and I naught is along OX. So we're getting this kind of a phasor diagram, which is a combination of all the phasor diagrams. Are we clear here? Yes? Alright, now why do we do this? Why do we club the phasor diagrams together? You see, there are many ways of finding the EMF in the circuit, but the most convenient way is by using the phasor diagram method. That is the most convenient and that is the most easy way. Okay, so we have to club the phasor diagrams of all the three elements. So having done that, we are getting this kind of a diagram. All right, now phasors are basically vectors, right? They're basically vectors. So basically here, what are we having? We have three vectors. Let me draw it with light blue. So we have three vectors. One vector is acting this way. This vector is VL. Another vector is acting along the same line this way. Let's make it a little bit short. Okay, that is not exactly going from this line, so I have to be very careful here. Okay, so let's say another vector is coming this way. This vector is VC bar, and another vector is coming from here that way. This is VR bar. Now listen carefully. This is the same diagram as this. All right, so basically if you have three vectors acting at the same point, how will you get the resultant vector? Very simple. What you need to do is you find the resultant of this vector and this vector first. All right, and here we assume that VL, the magnitude of VL is larger than the magnitude of VC. Okay, so that can be seen from the diagram. I have drawn the vector OB, which represents VL, longer than the vector OC, which represents VC. Got it? So we know that if two vectors are acting opposite to one another, their resultant will be VL minus VC. Yes or no? That is from the theory of vectors. Got it? Let me explain here. Suppose I have two vectors. So I have two vectors. This is, let's say, A bar and acting at point O, and this is B bar. They are opposite in direction acting at the same point, making an angle 180 degree with one another. Then what will be the resultant of these two vectors? It will simply be the longer vector B bar minus the smaller vector. So similarly here, since these two are acting directly opposite to one another, the resultant of this vector and this vector will simply be the larger vector minus the smaller vector. Is this clear here? So it will be VL minus VC. So VL minus VC, if you take, you will get a vector somewhere here, which is VL minus VC. Are we clear here? What will be the direction? Like here also, no? If you take B minus A, where is B minus A? It will be pointing in the direction of the longer vector, right? So this will be B minus A bar right here. So since VL is larger, the resultant of VL and VC will be in that direction, okay? Pointing in the direction of the larger vector VL. Is it clear here? So we have found the resultant of VL minus VC. So we are left with this vector and that vector. So what do we do now in order to find the resultant of this vector and that vector? We complete the parallelogram. Yes or no? We complete the parallelogram. We draw from here a side parallel to the opposite side. From here, a side parallel to the opposite side, right? Along the diagonal, that will be the resultant vector. Okay. All right. So this vector here, it gives the resultant EMF due to all the EMF across the three elements. So this is E naught out here. Are we clear on the theory? Right. So let us see how to do this. Okay. Let a pure inductor L, an ideal capacitor C, and a pure resistor R be connected in series as shown in figure 1. Where is figure 1? This one. All right. As they are in series, current at any instant through them have the same phase and amplitude. Let the current be given by this equation. I is equal to I naught sine omega t. That is equation 1. Okay. The voltage across each element, however, bears a different phase relationship with the current, right? That is evident from here, right? The voltage and the current, it has some phase difference between them. Number 1, the maximum voltage across L is VL is equal to I naught XL, right? This is from Ohm's law, V is equal to IR, right? Here, XL is the reactance, which plays the same role as resistance, okay? Which is represented by the vector OB. Where is that vector? This vector, OB. This is VL. The maximum voltage across C is VC is equal to I naught XC. What is XC here? That is the capacitive reactance, which is represented by the vector OC. Where is that vector? This one. OC represents VC. The maximum voltage across R is VR, which is equal to I naught R, represented by the vector OA. Where is that vector? This one. OA, it represents the vector, the voltage VR. Okay. Let VL be larger than VC. We're just assuming. Okay. Then their resultant will be VL minus VC. I think this is clear, right? It should be VL bar minus VC bar, which is represented by the vector OB dash. Where is that vector OB dash? This is the vector OB dash. Understood? Just like this one. The resultant of VR and VL minus VC is equal to the applied EMF E naught, right? So represented by the vector OK. Which vector? This one. OK. All right. So now let us find the expression of E naught. So in figure 2, how do we get the value of E naught? The value of E naught means the length of the vector OK. Very simple. Since this is a right-angled triangle, we are going to use the Pythagoras theorem. Okay, so basically OK square will be equal to OA square plus AK square. That is what we are going to write. Okay, so in figure 2, we have OK square is equal to OA square plus AK k square, right? But what is OK? OK is nothing but the magnitude of E naught. So this will be E naught square. OA is the magnitude of VR square plus AK. AK is the magnitude of OB dash. That means VL minus VC. VL minus VC whole thing square. Okay, so from here you can get E naught square is equal to what is VR square? Let us put a value of VR. VR is this, right? So this would be I naught square R square plus VL minus VC. VL is I naught XL, VC is I naught XC. So I can take common I naught, but there's a square here, I naught square. So inside bracket, I will get XL minus XC whole thing square. Are we clear here? This implies E naught is equal to I naught square R square plus, I can take common here. Now let's do one thing. Let's use a different bracket. R square plus XL minus XC whole thing square. Okay, this will go inside of a root. All right, so I can take common I naught, yes or no, but since it is a square, I can take it outside of the square root. So inside of the square root, I get R square plus XL minus XC whole thing square under root. My square root doesn't look good. Let me draw a better one. Yes. So this expression gives this equation, it gives the expression for the applied EMF. Okay, let's call this some equation. Is this clear here? All right, now the total effective resistance of LCR series circuit is called impedance. Okay, denoted by Z. I think you know the meaning of impedance. Impedance means to impede. To impede means to what? To slow down or to stop. That is the meaning, okay? Or to resist. So basically, here we don't call it resistance, right? We give it a different name, impedance. So if somebody asks you what is the physical significance of impedance, impedance play the same role as resistance, okay? Only the name is different. Just to differentiate that here, it is the AC circuit, but resistance is a term used in DC circuit, okay? So impedance, we know that resistance is voltage by current. Yes or no? Here the voltage is E naught and the current is I naught. So from here we get Z is equal to, if we take E naught by I naught, take this I naught here, are we not left with this term in the square root? So we're getting R square plus XL minus XC whole thing square under a root. Okay, a very important, very important relation 3. Okay, now have a look at this diagram, this figure 2. So this EMF, if you look, it is leading the current by a phase of phi. Okay, so let us find the expression how we get this phase phi. So what we can do here, we can take this triangle OAK and take the tangent of phi. All right, so let's just do that right now. So let me take another page. Okay, so in figure 2, tan of phi is what? What will be tan of phi? Just have a look. Tan of phi will be perpendicular by base. That means AK by OA. But what is AK? AK is VL minus VC. VL minus VC by OA. OA is VR. VR. Understand? Or we can write tan phi is equal to, what is VL minus VC? Is it not I naught XL minus XC? And VR here is I naught R. So this I naught and I naught will cancel. So we get tan phi is equal to XL minus XC divided by R. Let's put this inside of a box. Is that okay? So therefore, the alternating EMF in the LCR series circuit would be represented by E is equal to E naught sine omega t plus phi. Three cases arise. Number one, if suppose XL is equal to XC, then tan phi, which is equal to XL minus XC divided by R, this will be 0. So this implies that phi is 0. What is phi again in the beginning? What did we say? Phi is the phase difference between the EMF and the current, yes or no? And if phi is 0, what does it mean? It means that the EMF and the current are in the same direction, are in the same phase. Okay, there is no phase difference between them, which means that they are in the same phase. And what type of a circuit has the EMF and current in the same phase? It is a resistive circuit. That means a circuit consisting only resistor. So therefore here the circuit is purely resistive. Okay, so that's the first case. Number two, if suppose XL is larger than XC, then tan phi is positive. Yes or no? Because XL minus XC would be positive, right? So therefore phi is positive. Now tell me, what is that circuit where phi is positive? Phi positive means, just have a look here. What does it mean? It means that this one, it is positive, okay, going like this, not down, right? Phi positive. So for what type of circuit? For an inductive circuit, you see. So therefore this means that the circuit is purely inductive, or inductance dominated. Inductance dominated circuit. Number three, if suppose XL is less than XC, then tan phi will be negative. I think that is clear, right? XL minus XC is negative. Therefore, phi is negative. And what type of a circuit where we have phi to be negative? This circuit. So this circuit is for this phasor diagram, and that phasor diagram is for a capacitor. The circuit is purely capacitive. Okay, or capacitance dominated circuit. All right, so these are the 3 points that I want to discuss in this video. Okay, so I want you to listen to this video carefully. Just the concept is a bit it's not so easy to grasp if you listen to it for the first time. But then how we derive, it's quite simple. Okay, we just use the phasor diagram, and then we will get the value or the expression for the applied EMF. All right.